Okay, let's do a little bit of math. Well, math never hurt anyone. So we're doing integration by parts. That's section 7.1. This is a big section. If you're taking a calculus class, you're definitely going to have questions from this section on uh, exams and quizzes and things like that. It's going to be a big focus for a little while. And it also is a technique that allows you to solve a lot of integrals. So it's kind of a go-to thing, and it's section 7.1. It's the first section in chapter 7, which is all about techniques of integration. This is the first one. Okay, uh, so here's our formula. It's a little bit of a weird formula, but we'll work with it, and then you get used to it. The integral of u dv is equal to uv minus the integral of v du. There you go. Well, how's that going to help us? Where does this come from, by the way? It comes from the product rule. So if you were doing an antiderivative of something, you wanted to find the thing whose derivative is what you're looking at. And let's say that thing you're looking at came from the product rule. If you took the derivative of the integral, you would get back to the things you started with. If it came from the product rule, then you're going to have to do your antiderivative and be able to undo the product rule. So let's just see how this formula comes about. If I have the integral of, or if I just have u times v and I take the derivative, I'm going to use this notation so it matches up with the integral notation. But remember with the product rule, you kind of do it by parts, right? You do u times the derivative of v plus v times the derivative of u. And then we can write that like this. Another form of v prime is dv, and then another form of u prime is du. So I have the derivative of u times v is equal to u dv plus v du. Now, if I integrate both sides, and I'm going to separate the integrals. If you have the integral of one whole thing, then you can break it into two. That's one of the laws of integration. V du. Okay, and then right here we have the antiderivative of a derivative. So you just get back what you started with. And now this is where we get our formula. If you solve for u dv, then that's equal to uv minus the integral of v du. Okay, and that's our integration by parts formula. Okay, well, having given you that, it doesn't really help because you need to practice it. That's the main thing. You need to see how that's going to be useful. So what happens is you're presented an integral, and in number one, you're given this integral here. And they even prompt you as to what to do for these first couple of problems. But basically, when you see the integral, you have to decide what to pick for u and what to pick for dv. This is your integral that you're given, u dv. So you have to say, okay, this part of the integral is the u and this part of the integral is the dv, and then we get all the rest of the parts of the formula as we go. You have to pick the u and the dv to get started. Okay, and in this problem, they suggested, they say let u equal ln x, and dv is x squared dx. And notice that we've accounted for everything that we have in the integral. There's the ln x, and then there's the x squared dx. Everything's been accounted for. So that's my u dv. Now I'm going to need v in my formula, and I'm going to need du in my formula, but I don't have those, and the way we get them is by doing the differentiation to get du, okay, and that's going to be 1 over x dx. And And then to go from dv to v, we're going to integrate, and that's where we get this integration by parts. We're doing part of the integration right now. So the antiderivative of x squared is x cubed over 3. I'm going to leave off the plus c. Okay, so now that we have all these things, let's use our formula. The integral that I'm interested in knowing, that's this one, x squared ln x dx. That's my u dv, and that's going to be equal to uv minus integral of v du. Okay, so the u and the v are right here. That's going to be x cubed over 3 ln x minus the integral, and then I have v du here. When I multiply v and du, notice that one of the x's cancels. And I get 1/3 x squared dx. Okay? And then to complete the integral, this portion is already done. I don't need to do anything else here, but I do need to integrate this. So when I integrate x squared, again, we just did it, so it's x cubed over 3, so I'll get minus 1/3 times x cubed over 3. Okay, and then this is an indefinite integral, so I need to put a plus c, and I'll write my final answer. It's going to be x cubed. We can even factor out x cubed over 3 out in the front, and then I have ln x minus 1/3 plus c. Okay, that's the first integration by parts. Okay, let's go to number 2. Number 2, they're trying to mix it up a little bit. You got theta in there, so you're kind of used to x, but now they give you theta, so you got to deal with that. Notice how in this integral you have the product of things, so that kind of clues you a little bit that maybe integration by parts is useful, because if you know that integration by parts is the undoing of the product rule, then when you see a product, well, that might be a candidate. It's not always the case, but that's just something to think about. So I do see a product here. It's theta times cosine theta. They prompt us as to what to pick for u and dv. They say pick u to be theta and pick dv to be cosine theta, d theta. And we need to account for everything. So I include the theta there, and that makes sense to have the d theta here, because I'm going to be integrating that. The dv becomes a v. When I integrate that, I get the thing whose derivative is cosine is sine. And then over here, when I take the derivative of u, I get d theta. So the integral I'm interested in, that's going to be my integral of u dv, and that's going to be uv minus the integral of v du. U times v is theta sine theta, and then integral of v du gives me integral of sine theta d theta. And we can integrate that. This is theta sine theta minus the thing whose derivative is sine theta is cosine theta. Well, we have a minus sine theta, so it's plus cosine theta. The derivative of cosine theta is negative sine theta plus a constant. Okay. Now, I also want to introduce a shortcut, because I'm going to be doing this in several of the problems. I want to show you a quick way of doing this. So, excuse me. We already have the answer here, but let's do this another way. We're going to do theta cosine theta d theta, and I'm going to pick my u to be theta and my dv to be cosine theta. And what I'm going to do is I'm going to differentiate this side because that's what I do. If you notice what I did there is when I picked u to be theta, I did differentiate it. So this is my differentiate side and this is my integrate side. And what I'm going to do is I'm going to differentiate this guy right here all the way down to 0. So the derivative of theta is 1 and the derivative of 1 is 0. Oops. And over here, I'm going to integrate as many times as I need just to match up with the differentiation. So the antiderivative of cosine is sine, and the antiderivative of sine is negative cosine. And you notice that that's what we ended up doing in this problem here. When my first integration was right here, and I went from cosine to sine. I did the antiderivative of cosine. That's what I just did here. And then in the next step, when I had my second integral here, I did the antiderivative of sine, and that's what I end up doing right here. So you see, I'm putting all the pieces in that I used anyway when I did the solution. Now the answer to my integral here, this integral, is what we're going to do is we're going to match up close. I think some people call it a shoestring method, but they don't go straight across. But if you look at the this minus, this isn't a minus here. That's just a tick mark. Okay. So what I'm going to do is I'm going to multiply these, and that'll be my answer. And what I have to do is I have to alternate signs. So the first one's going to be a plus, and then I'm going to introduce a minus in the second one. If I kept going on this, it would be another plus after that. Okay, but anyway, if you look at what the answer is, if I just do this, if I combine these two, I get theta sine theta. And then I have, this is a minus right here. So this second one, it alternates. So even though I get 1 times negative cosine theta, I'm going to add another negative, so it's plus cosine theta. And that's the answer that I got. If you look above there, that's the answer that I got. So you see, that's a little bit of a shortcut, and it's pretty useful when we have integration by parts. Sometimes you end up doing it twice, so I just wanted to introduce that one, a nice easy one, and we'll practice it on each one as we go here. But it's a nice little trick, and they don't even put that in the book here. But you know, if you're taking a calculus class and you have that trick and the other kids don't, you'll get a little advantage. Okay, number 3. You know, number 3 is red in the book, and I think the reason it's red is because if you go online, you can find solutions to the red problems on their website, you know, the website for this book. But a good way for you to interpret the red problems is those are good test questions. Those are the kind of things that'll show up on your exam if you're taking a class right now. Okay. Anyway, so here we go. Again, we have a product of two things, so that's a hint that maybe we're going to do integration by parts. I think a bigger hint that we're going to do integration by parts is that it's in the integration by parts section of the book. So let's do integration by parts. And it's going to be similar to the previous one. We're going to pick u equal to x and dv equal to cosine 5x dx. what we need to do, remember, you need to account for everything. So I have accounted for everything. I've got the x and I've got the cosine 5x dx. Over here, we're going to take the derivative and we're going to get du, which is 1 dx, or just dx. I'm just going to write dx. And then from dv, we get v by integration. So, you don't want to have to go over and, look this whole thing up on the Encyclopedia Britannica, if you even know what that is. I guess it'd be Wikipedia these days. But, so this is cosine 5x, and what you want to be able to do this quickly so you don't have to, go and do a u substitution for this. So what you say to yourself is, okay, what's the thing who gives me, whose derivative gives me cosine? Well, that's got to be a sine, right? And if I got cosine 5x for my derivative, well, I better have had sine 5x. But if I had sine 5x and I took the derivative, I would get a 5 out in front, right? When I took the derivative. And I don't want that. I would get 5 cosine 5x, right? And I don't want that, so I have to put a preemptive strike in there and put a 1/5 for that 5 that's coming when I take the derivative. You see, I want the thing whose derivative is cosine 5x. Sine 5x is the thing that gives me cosine 5x. The problem is I get this extra 5 when I take the derivative because of the chain rule. So I'm going to put a 1/5 out there to compensate for that, so that when I take the derivative of v here, I get dv. Okay, I hope you're able to follow that. Now, because you don't want to sit here and do a u substitution, it just takes too long. Plus, you already have u's already. Okay, anyway, so let's do our formula now. The integral we're interested in, x cosine 5x dx, that represents the u dv in my integration by parts formula. And the u dv is equal to uv minus the integral of v du. Okay, so now I'm going to write those things in. uv is x over 5 sine 5x, and then minus the integral of v du. So that'll be 1/5, and then I have sine 5x dx. Okay, now let's integrate that. This one doesn't need any more integration. This one's done. Okay, and then I have minus 1/5, and then the antiderivative of sine 5x, you see I already did it right here, or something like it. Okay, so the thing whose derivative is minus sine 5x is cosine 5x. But then I need another 1/5 out in front because, ignore this 1/5 right here for the time being. Now, I also have to put a plus here, okay, and here's why. Because this was a minus, the antiderivative of sine is negative cosine. So that's where that minus comes in. And then, because it's sine 5x, I need to get back to that. When I take the derivative of cosine 5x, I would get an extra 5 out in front, so I need a 1/5. That's independent of this 1/5 right here. Okay, anyway, so that's our answer here. It's going to be x over 5 sine 5x plus 1 over 25 cosine 5x plus constant. Okay. Now, if you're learning this, trying to learn it, go and take a clean piece of paper and reproduce that problem without looking at the solution. Push pause on the video and go reproduce it yourself. That's the way to go. Okay, number 4. Well, maybe I want to do that other one with the shortcut. I think I do. So let me just do the shortcut for that one. All right, so the integral was integral of x cosine of 5x dx. Okay, and so what I'm going to do is I'm going to put x here, and that's my differentiation side. And then I'm going to put cosine 5x here, and that's my integration side. And I'm going to differentiate x all the way to 0. Now, some of you might be thinking, well, when can you use this trick and when can you not? You need to be able to differentiate all the way to 0 to use this trick. And so that's why this x affords us the opportunity to do this. Okay, I'm going to differentiate x, I'm going to get 1. Differentiate 1, I get 0. Now I'm going to match those with integration on this side. The antiderivative of cosine 5x is 1/5 sine 5x. And the antiderivative of 1/5 sine 5x is negative 1/25 cosine 5x. And remember, the thing whose derivative is sine 5x is cosine 5x with a minus. And but because of the 5x, you need an extra 1/5 out in front to compensate so that you get back to the original. Okay, now the way we write our solution is these little diagonals, and then this is a plus and this is a minus. So when I write that out, I have x over 5 sine 5x, and it would be a minus 125 cosine 5x, but this minus right here, that causes it to be plus. And that's because in the integral formula, we have this minus here in the integration by parts formula. So we got the same thing. And that's a little easier, I think. But you still need to practice the integration by parts method because that technique doesn't always work. It works with these first simple examples. All right, so actually maybe I'll do that first for number 4. For number 4, I have integral of y e to the 0.2 y dy. All right, look at that, 0.2. Boy, they talk about trying to confuse the enemy. All right, we got to deal with the 0.2. Don't worry about it. It's just a number. Might as well be a 5, but it's not. It's a 0.2. If it helps, but make it a 1/5. Somehow the decimal makes it look pretty ugly there. Okay. Anyway, let's do our shortcut. If I pick y to be the differentiation stuff, and then e to the 0.2 y is my integration side. So this side I'm going to differentiate all the way to 0, and here I'm going to integrate all, and match it. Put it 0.2. Okay, differentiating y, I get 1, and then the derivative of 1 is 0. Okay, now here I have to be a little careful. So the thing whose derivative is e to the 0.2y definitely has to have an e to the 0.2y in it, because the derivative of that is going to be e to the 0.2y. However, if I take the derivative of this, I would get an extra 0.2 out in front, and I wouldn't get back to this one, right? So I need to divide by 0.2, which is the same as multiplying by 5. So let me just explain. So 0.2 is equal to 1/5. So 1 over 1/5 is 5, and that's why I have a 5 out in front. So I'm really doing 1 over 0.2 there, so that when I take the derivative, I get back to this one. Okay, now I'm going to do this again. So the antiderivative of this guy is going to be 25e to the 0.2y. And that's for the same reason. If I just integrate this part, I get 5e to the 0.2y again, and then I multiply by the 5. So that's how I get 25. Okay, and now I'm ready to go with my answer. Remember, it's plus minus. So my answer is 5y. Oh, technical difficulties. I have 5y e to the 0.2y minus 25e to the 0.2y plus a constant. Okay, there we go. And maybe I just do it that way. Just do this the shortcut approach for that. We'll get plenty of practice doing these as we go. Okay, let's do number 5. Number 5 also sets itself up nicely for this shortcut. T e to the negative 3t dt. So again, I'm going to pick t to be the side that I differentiate all the way to 0. And then the rest of it, I have to account for everything in the integral. So the negative e to the negative 3t, I'm going to integrate to match the t. So the t derivative is 1, and then the derivative of that is 0. When I do the antiderivative of e to the negative 3t, the thing whose derivative is e to the negative 3t is e to the negative 3t, because that's what you get back again. But if I took the derivative of this, I would get a negative 1/3 out in front. I would get a negative 3 out in front. And so I need a negative 1/3 to compensate for that so that I get back to this when I take the derivative. So that's the antiderivative. And the antiderivative of this guy will be negative 1/3 times the same thing again. So it'll be positive 1/9 e to the negative 3t. And you can take the derivative of this just to make sure that you get back again. All right, and then we line it up diagonally and remember our plus minus. So our answer is negative t over 3 e to the negative 3t minus 1/9 e to the negative 3t. And you can factor out the e to the negative 3t if you want. Okay. Okay, number 6. Number 6. Now they're starting to get into the confuse the enemy realm. And they're adding a little spice to everything. Instead of it just being sine x, now we got sine pi x. And instead of it just being an x out in front, now we got x minus 1. Now you could multiply this out and do 2 integrals, but let's just use the technique that I've been showing you here. So if I do x minus 1 and I differentiate that all the way to 0, I get 1 because the derivative of x is 1 and the derivative of negative 1 is 0. And then the derivative of 1 is 0. And then on my integration side, I'm going to do sine pi x. Okay, so be careful here because the antiderivative, the thing whose derivative is sine pi x, well, you better have cosine pi x. However, if you take the derivative of cosine pi x, you will get negative sine. So I need a negative out in front. And I will also get an extra pi out in front from the chain rule. So I need a 1 over pi to compensate for that so that I get back to the sine pi x. Okay, now the antiderivative of this term here is going to be, well, the antiderivative of cosine is sine, so I'm going to have a sine pi x. But if I took the derivative of that, I'd get an extra pi out in front, so I need another 1 over pi. So I have a negative 1 over pi squared here for this term, because I already had a negative 1 over pi, and I got another 1 over pi for the antiderivative of cosine pi x. Okay, now I'm ready to go. And you see how quick that was? Oh, don't forget your plus minus here. So the answer will be negative x minus 1 . I'm going to put the 1 over pi out in front. So negative 1 over pi x minus 1 cosine pi x plus, it's a plus because I have a minus here and a minus there. So plus 1 over pi squared sine pi x plus a constant. Okay, now see how quick that was with the shortcut? I could do the whole thing for you with the integration by parts, and I probably should just because you need to practice it, but it's really a lot longer, and I'm not going to do that because you have your answer, and you should practice that yourself. That'd be a good thing if you're new to this. Go do that by yourself and see if you get the same answer by setting this equal to u and this equal to dv and doing your integration by parts from that. Like I said, we'll get plenty of practice on the integration by parts, um, so I don't feel like I'm shortchanging you by doing this shortcut. In fact, the shortcut's very nice, and I want to show that to you because um, the book doesn't even have it in there, and it is a pretty nice technique. Okay, I didn't put the number here. That was number 6. I think I'll stop now. I think the video is long enough. Okay, so I'll see you on the next video.